This is a brief intro to Python objects and classes. An object is a bit of data you want to manipulate. It would have a set of characteristics, for example a musical note, which would have pitch and duration and maybe an amplitude waveform. You would write a class which describes these characteristics, or maybe you would import the class from a library if someone else had written such a class. You then create individual notes, the objects, which are instances of the class. The class provides a way of creating these objects. Once created, it is up to you what you do with them. Perhaps play them or assign them to instruments, which may be further objects defined by their own class. So objects and classes are applicable to anything. They could be location points in a map, images, velocities, money. They're pretty useful. So the top half of the screen is a script and the bottom part is a Python shell. So the script can be run and the variables will be available in the shell. So starting with a simple built-in object, the string. I've set a variable a equal to the string hello, and looking at the type of a, you'll see it as a class of str. But it's a fairly complicated object. It's a sequence of characters and, using square brackets, individual characters can be accessed via indexes. Again, this mechanism is defined in the class of string. Strings obey addition, in which case two strings are strung together. It is also an iterator, so the for statement can iterate over each of the sequence members. If you add an object such as an image, you may want to be able to iterate over every pixel. The built-in function len works and gives the length of the string. If you created your own object, the question arises, how would the len function know how to work with it? Come to that, how would addition work? The string has methods, which are functions bound to an object, and are called by object.method. In this case, the lower method returns a lowercase copy of the string. That's quite a lot of functionality for a simple string, and you may want to include that same sort of level of functionality in your own objects. Before we get on to defining classes, a quick look at defining functions. Here we have two. One calculates the area of a triangle, and the other adds two strings together with a space between. A function is a callable object. When called with brackets and arguments, it returns its value. And I can illustrate that by showing the value of x and y. But the function itself, without the brackets, is an object, just like any other object, but with a mechanism that makes it callable. As it is an object, it can be assigned to a variable like any other object, or put in a list or even passed as an argument to another function, which is sometimes useful for event-driven programming, where a function can be passed to a routine that then calls the stored function whenever an event occurs. So here I assign triangle to the variable z. This means z is now the same function, and can be called with brackets and arguments just as triangle can. So at last I'll define a class. Here's a really simple one called square, and its contents is pass, which means do nothing. So the only thing it has going for it is its name and any default functionality built into all classes. It's called square since this could be part of a drawing package or maybe a mapping program. As an example, it's something easy to visualize. The class can be called rather like a function is called, and it returns an instance or object of its type. You'll see that square is a class and the two instances of this class, x and y, are both objects. The number shown is the object's ID, which in the standard version of Python is the object's address in memory, which you can see are both different, showing they are two different objects. Next you'll see that I've given the objects an attribute, which is essentially just creating a variable like any other variable, but binding it to the object. This is done with the dot notation. I've called the attribute width simply because a square has width. The width attribute can be changed, just like any other variable, but the width of x and the width of y are two different things. Changing one does not change the other, so you can consider these as two separate squares, each with their own width. More complex objects will have multiple attributes. The Python standard library defines a datetime class that has attributes year, month, day, hour, etc. So here I've defined a method, area. Python uses indentation to define code blocks, so defining area inside the class definition sets this as belonging to square. Methods can take multiple arguments, but the first argument will always be an object of the class, which is set into the variable name self. It could be given any name, it's just a variable, but by convention it's always self. So this script first creates an object x and gives it a width of 5. The first way of calling the method is simply square.area and inserting the object x as the argument value. Inside the function this becomes self, and the function calculates x.width times x.width, being 5 times 5, and returns the area, 25. The more usual way, however, is calling x.area, which simply returns the area of the x object. But how does that work, and what has happened to self? In this case, the Python language does things for you. It recognises x is an instance of class square, and area is a method of that class. So it takes x and automatically inserts it as the first argument of the method. It's interesting to look at the type of area. When it's square.area, it's just a function, and you have to insert x into it, as with any other function. However, when it's x.area, it becomes a method bound to the instance x, and will insert the x for you. All this is nice to know, but the effect is that using methods is simplified. Python has special methods, which apply certain actions to the class. These special methods always have names starting and ending with double underscores. I'll cover a few, but there's lots of them. The internet is awash with information about them, sometimes called dunder methods and sometimes magic methods. The one you'll see most is init. This is the initializer and is automatically called whenever a new instance is created, with arguments taken from the class arguments. In this example, init creates the width attribute, so you don't have to. Setting up initial attributes is typical of the init method. The 5 set here when creating x is passed to the init method and sets x.width. Similarly, the 10 sets y.width. The end result is you have objects set with their initial attributes. So creating a new object is simplified, and I'll just create a new one, z, with width 8. So though the class is becoming more complicated, using it is becoming easier. Typically, if you imported a class from a package, its documentation would tell you the arguments and the attributes they set. Python has built-in functions, such as len for length and str for string. Typically used for converting a number to a string, it also has operators, such as addition, multiplication and comparison operators used in if statements. This shows how str and equals are handled. Should the str function be called with an object as its argument, then the object's class will be checked to see if dundastry has been defined, and if it has, that will be called. So in this case, dundastry returns a string describing the object, a string of object brackets with close brackets. In most programming languages, the double equals operator is a comparison. If two values are equal, it returns true. If not, it returns false. So for your own objects, you can invent your own decision on whether objects are equal or not. The equals comparison operator calls the dunderEqua method, which has arguments self and other, where other is the other object being compared against. By writing the dunderEqua, you are deciding how objects are compared. In this case, it seems sensible to say two squares are equal if they are of the same width. There are similar dunder methods for greater than, less than, greater or equals, and so on. So if you are creating objects that will be ordered or compared, you have all the facilities to do so. A function is called by the function name with round brackets that contain any arguments to the function. So in this case, the function is said to be callable. So being callable is a characteristic of an object, just like any other characteristic, and using dunder call makes the object callable. In effect, the object will then behave like a function. I had a hard time thinking of why you would want a square to be callable, and frankly, in the end I couldn't think of a real-life example. So instead I've shown a rather artificial example of it just taking an argument, multiplying it by the square's width, and returning that. It's interesting that by changing the object's width, you can change what calling the object does. It becomes a function which can be adapted by altering its attributes. The call capability might be used in a situation where you want to simplify the usage of an object. For example, instead of calling x.area to get the area of the square, you just call x brackets to get the area. Right, a brief jump into decorators. You don't need to follow the details of this, it's just useful to know they exist. Essentially, a decorator can be applied to a function, and it then alters the function in some way. This example takes the function triangle, which calculates the area of a triangle, and applies the log decorator to it, which then logs every time the triangle function is called. In this simple example, it doesn't log it to a file or anything, it just prints now logged. The point is that rather than put a load of logging logic into the triangle function, we can keep it clean and put the logging somewhere else, and the log decorator can be easily added or removed and applied to other functions as well. So a decorator manipulates a function in some way. What it is actually doing, if you're interested, is the decorator is a function that accepts the original function as an argument. It then creates a new function, which generally implements any extra work required, and also calls the original function. It then returns that newly created function. Applying the decorator with a hat syntax replaces the original function with the new one, and in this case, triangle now magically has the extra logging capability. So why this digression into decorators? There are some alterations to methods which can be done which are fairly complicated. So there are a few decorators built into the Python language which can be applied and which spares you the details. So here's our first use of a decorator. If you look at the area method, you'll see it has a property decorator applied. This is a Python language built-in decorator which is used to make a simple method look like an attribute. So x.area, without any calling brackets, is equal to 25, looking just the same as if it was a normal attribute variable. This only works if the method doesn't require any additional arguments, nor is it the full story. There's an extra method and decorator needed if you want to be able to set the area value, which in this case involves taking the square root to get and set the width. I'll not cover it here since it's going into too much detail for this introduction. So why would you bother with this? One reason may be to simplify the usage of a class. You can just use an attribute. In general, if the method is computationally intensive, it's better to emphasize that it is a method. But if it is very simple, then having it look like an attribute makes using it a bit less verbose. Another built-in decorator is class method. By convention, instead of using self, the first argument is set to CLS, which in this case will become equal to the class square. So you can call it by calling class.method rather than object.method. So in this example, square.fromArea. Oh, I forgot to run the script, just a second. A typical use is to create an alternate way to produce an object. Normally you create a square object by providing the width, but in this case, by calling square.fromArea, you can supply an area value. So in this example, fromArea works out the width by taking the square root of the given area, and then it generates a new square object using that width and returns the new object. The end result is you have a square object produced from an area value rather than a width value. One example in the standard library is the datetime class. Normally you create a datetime object by calling date time with year, month, day, etc. as the initial arguments. But datetime has a now class method, so calling datetime.now looks up the system date and time and returns a datetime object of the current date and time, which is very convenient. Another decorator is static method. This provides the class with a straightforward function. It can be called with the dot operator on either the class or an instance of the class. It is the equivalent of any other function defined outside the class, except it is bundled along with the object. So in this example, a square root method may be useful in a library containing square objects. So it's given in the same way a sandwich may be put in a toolbox. It could be useful. When a class is provided in a library, this is a useful technique of providing related functions which will be available to anyone using the class. So going back to special methods, adding two integers is straightforward. Adding two strings is just a matter of stringing the two together and returning a new string object. But how about adding two of our square objects together? You can define the special method dunder_add to do it, and it will be called whenever you try to add two squares together. It's up to you to define how add works for your particular object. In this case, we'll add two squares by returning another square which has an area equal to the sum of its two components. So it's just a matter of defining add. So x is a square object, y is a square object, and adding them gives z, which is another square object. The area of z is 25 and its width is 5, which is what you'd expect as 3 squared plus 4 squared equals 5 squared. This has just illustrated Pythagoras. There's similar special methods for subtraction, sequencing, iterating, and other operations you may want to do for your objects. The other major feature of classes is inheritance. You can build a new class that has all the features of an existing class plus some extra capabilities. Here I've shown the simple version of square again, with the width property and area method. A new class cube is created, and the class uses the argument square to indicate it is inheriting from square. It automatically contains all the square methods. The original dunder_init method is okay, it just sets the width, but the area method has to be updated, as the cube surface has 6 faces. So by defining a new area, we replace the existing area method. You'll notice inside the area method we can still call the area method of the parent class by using the built-in function super. And we can also include new methods, in this case volume. It's quite typical to have a tree of classes. So if you have a family of classes, their common attributes and methods can be defined in the parent, and the more specific methods defined further down the tree. And that's it for this introduction. I hope the video was useful.